Okay, I'm just going to talk for a few minutes. We'll go to group work and I'll stop recording. But, oh, and you know what, I need to share. So this is one problem, I need to share something different. Okay. Probably should just share the whole desktop is what I should do. But, okay, sorry, it's early in the semester, I'll get used to this. Hopefully it won't be all the tech stuff we'll get used to. But, okay, so I talked a little bit about 3D space just for a few minutes in class on Wednesday, right? And yeah, we have, like I sort of said, we'll draw the axes like this and think of like the XY plane as like the floor of this classroom and the positive Z axis going straight up vertically. Right, this is just a convention that we tend to draw the Y and Z axes in the, that's like the plane of the paper, and then the X axis is coming out and poking you in the eyeball. Right, does that make sense? You just can't, if I drew that literally, you wouldn't see the X axis. It would just be a point. So it has to be kind of from a perspective, like, remember how there's quadrants in the XY plane, like first, second, third? This is sort of the first octant where X, Y, and Z are all positive. I don't know the names of the other octants. I don't know which one's the second and third and fourth and fifth and sixth and seventh and eighth. Eighth is probably all negative. Well, maybe not. The fourth quadrant's not all negative. Doesn't matter, nobody names the octants. Nobody numbers the octants. But the first octant's clearly the one where X, Y, and Z are all positive. So it's almost like you're taking this view from the first octant towards the page. And I guess, we'll get into group work very quickly, but it's fun to start to try to draw this stuff because there's this issue of like all these little, like this is clearly a right angle, but I claim these other two are right angles also, even though they don't look at it. It's like a perspective drawing thing. It's one thing you can work on in this class is your drawing of 3D objects, Let's see, so then, oh yeah, and so then I think I said this on Wednesday also, that if you, instead of pointing the X-axis at your eyeball, if you point the Z-axis at the positive Z-axis at your eyeballs and look down, you are seeing the XY plane the way we usually have it. X going that way and Y going that way. But that is a bit of a convention. So I'll just say this and then we can get into group work, but I said, remind me to discuss it in class, and it's on the screen, so I'll just discuss it in class. So we could have just as easily decided to make the Z-axis, the positive Z-axis go down, or maybe like switch the X and Y axes or something, like it's a bit of a convention that we did this, but it's a convention everyone uses. And it's basically a right-hand rule. And these come up a lot in this class when you're in 3D. If you've ever taken a physics class and talked about a right-hand rule where you have like, what is it, like a electric current created a magnetic field or something. Something like, yeah, something like this, a lot of this. Actually, and I'm left-handed, so it's, I have an advantage over you righties, that some of you are lefties hopefully, but advantage that I can do the right-hand rule and write at the same time. So, yeah, so the right-hand rule here, the way it works here is that, and the way this will work sometimes, we're going to talk about vectors a lot in this class, and vectors are basically just arrows. And there's sort of 3 arrows in this picture, right? The positive axis, each one. And if one of the versions of the right-hand rule is if you point your fingers in the direction of, say, the first arrow that you want to think about, like the x-axis. So point your fingers on your right hand that way, and then curl them towards the second one, the y-axis. Then your thumb is pointing in the direction of the positive z-axis. Right, whereas if I point my fingers at the y-axis first, and then wanted to curl them towards the x-axis, I'd have to do this to curl them towards the x-axis, and my hand would point down. So there's sort of a right, so that's kind of the right-hand rule of like which way the z-axis goes. Not that it's that hard to remember, but we'll see right-hand rules come up later in the semester, so I thought I might as well throw it out there immediately. But yeah, like you just have to get used to that a little, like fingers in the direction of the first arrow, curl towards the second arrow, and then your thumb goes in the direction perpendicular to those two by some right-hand rule. and if you did the opposite order. It's actually one of the things we'll see, one of the first operations we'll see in math that's non-commutative, where the order matters. If you do, because if you do X and then Y, your thumb goes this way. But if you do Y and then X, your thumb goes that way. So you're very used to being able to do things in either order, like add or multiply numbers in either order. But as you go up higher in mathematics, you start seeing more and more operations that are no longer commutative, no longer where the order does matter. Although it just picks up a plus or minus. So, okay, cool. All right, so now I guess what I wanted to do, and again, there's this issue with COVID of like how comfortable people feel doing group work. I love having all these blackboards. I think it's very nice to like divide you up into groups and have you guys stand at the board and like talk out stuff and write it down. And I'll talk a little bit about group work, but about how I think it works well. But I'd like to break up into groups. One thing that didn't occur to me until just now is that I got used to clicking Zoom rooms and just assigning you all to Zoom rooms. And now that's actually, I have to actually assign people. I have to actually put people in some sort of groups. This out of the way so some group can use this board if they want. But maybe, I think what I used to do is like line people up by like some alphabetical order, like what state you're from or country, what your favorite color is, what your favorite sport is, whatever. Everything's weird now because I don't know whether to make you guys move around and get close to each other. It's a little strange. So maybe I'll just, wait, let me see. I think there should be about 30 people here based on the class registration. Let me just count real fast. 9, 12, 15, 18, 21, 24, 27, 29. Oh, and I'll have to talk to the person on remote and see how to include them also. But okay, so yeah, and then there's 9 boards plus the front. Maybe I can make 9 groups, 2 groups of 4, and 7 groups of 3. No, that doesn't make sense. Does that make sense? Does that have to 29? Sorry? Yeah, 29. 2 groups of 4, 7 groups of 3. Your first math test of the semester. Thank you. Okay. So yeah, why don't we make, so then that would be, I guess that could be 2 on each side of the room. 2 groups on each side of the room. Did I say 8 groups? I said 9 groups. Okay, never mind. I'll try to figure this out. Maybe you 4 could go to that board. And like I said, you can pull this up on Blackboard. I'm just gonna ask you guys to start with number 2 and start working through it and talking it out. So maybe you 4 can go to this board. Oh, actually, sorry, before you go, and before I start assigning everyone, group work in general, since this is the first time this semester, introduce yourselves, say hi. You wanna be personable, right? I really like when students work on the boards, like some students want to sit down and just like write on their notebooks. So what I would recommend is that you alternate sort of who's writing on the board. You like switch out so the other people can write stuff down on their notebooks, you know? So I recommend that. And then I also just have a general like, don't be an a-hole policy of like, some people like want to show off and show how smart they are and go off and do all the problems really fast. And you're a little team, you're a team, and different people think through things different speeds. And if you think you figured something out, you might A, hold back a little bit, and B, like just feel like it helps both of you if you try to describe what you think you figured out and the other person trying to listen, you know? So like, just have some team solidarity and try to be nice to each other and work with each other. That's my general group work advice. But introduce yourselves and say hi. I'll try to go around and get to know you guys too. So hard with the masks. I'll probably ask all your names 8,000 times. I can kind of recognize the students that I know already. That's about it. Okay, so you 4, this board. Maybe you 4 back here, this square. Maybe that middle board. So that was the 2 groups of 4. So maybe you 3, 1, 2, 3. The back left, back ball, left side. I think I put him with you're with U3, back middle. U3 can be at the front, or maybe the front right, that little board over there. U3 can be the front middle or kind of under this screen. U3 here. Am I down to 6? Okay. U3 can be right there, and U3 can be back there. Again, if you have any discomfort with being close to people, like feel free to try to hang back a little bit, or if you want to really just like work yourself. So just start talking through the problems. It might be good to pull up the PDF so you can scroll through it, at least somebody's screen. Oh yeah, introduce yourselves, and I'll wander around. Tatum? Hi. You know, it's funny. I don't know. I guess you're like taller than I don't. When you see someone on the screen, you don't know. I'm probably shorter than you thought. I know. I think I saw you walk out of class on Wednesday, and I was like, oh, she's tall. In person, it's so weird. Oh, let me talk to the person. Oh. Sorry, let me. I'm gonna stop recording the Zoom. My mic is still on. Hello. All right, guys, that was fun. Yeah. This group's work is now immortalized on the recording. Congratulations. So, okay. So if you're watching at home or watching the recording, please have the PDF pulled up of the 3D space. Actually, let me switch back. So I don't really want to be on the screen. Okay. So, but yeah, you can't see this file now, so I'll be referring to problem numbers. All right, so just some of the things that came up. You know, this number 2, to me, sort of this -3, -2 point was kind of almost right at the origin, like behind the origin, which just shows you the difficult nature of trying to draw 3D points on a 2D picture, right? So there's always some issues we're going to have there. Right, you've seen that, like, I'll write some of this down. Here's my special chalk. So yeah, I mean, so we've seen like the XY plane. I think most of you or all of you got that the equation is z = 0. The equation of the XY plane. So that's like, because every point on that plane like satisfies z = 0, right? So that's actually an equation for the plane. It's analogous. A lot of times you should think, what's the analog in 2D, right? And the x-axis in 2D is just the equation's y = 0, right? So this is like z = 0. The xz plane is y = 0. The yz plane x = 0. If you wanted something like the x-axis, you'd have to say both y = 0 and z = 0. And this is sort of interesting already because in 2 dimensions, when you have an equation, it just traces out some curve, right? But here now it's like one equation traces out a surface. But if you want to get a curve, you almost have to have like 2 equations that intersect. It's almost like you can think of this as the intersection of the xz plane and the yz plane. The x-axis is like the intersection of the, wait, not that, what did I say? Sorry, the xy plane and the xz plane, right? The intersection of the floor and that wall. And so that's already something interesting that's going to come up a lot, is like for surfaces, you usually have one equation, but if you want a curve in three-dimensional space, you either need two equations, or you could sort of describe it, what we're going to call, this is going to come up a lot this semester, and don't worry too much about this word yet, I just want to stick it in your head. We can describe this parametrically, so a parametric equation, as the set of points x comma 0 comma 0. Like just, that's kind of a natural way to describe the x-axis, right? Just a set of points x comma 0 comma 0, where, and this thing is called the parameter. Like this can be any value. Parameter can take on any value. So we will think a lot about parametric equations, because if we ever want to describe curves in space, we're going to need to, we're probably going to do it parametrically rather than as intersections of, like if you have some complicated curve, it's going to be kind of hard to find it as an intersection of two surfaces, but we might be able to just describe the points. So this word, we're going to talk about that a lot. So don't worry too much about it. Okay, so that's the first thing. Just because we're going to run out of time quickly, let me move ahead. So in terms of distance stuff, I like this argument if you drew the two triangles and realize it's just kind of like a 3D version of the Pythagorean theorem, that the distance from the origin to the point x comma y comma z is just given by the square root of x squared plus y squared plus z squared. Again, it's a perfect analog of the 2D of the 2D situation, where you just stick in the z squared. Yeah. It's gonna be the same. Yeah, for like in dimensions, it's just gonna be like x1 squared plus x2 squared up through xn squared, square root of the whole thing. So distance. So there's some students thought, well, maybe it should involve like a cube root or something, and which is natural to think if you're going to generalize dimensions, but it turns out no, it's nice. It's just you just throw out square roots. And then when you want something like the equation of the sphere, well, that's just all the points, like this number 9, equation of the sphere of radius 5. Well, it's all points. Well, radius 5 centered at the origin, right? Yeah. 5 centered at the origin. It's all points x, y, z such that the distance from the origin to x, y, z is 5 equals 5, right? But that is really just saying that this expression right here equals 5. So I'm going to run out of space. Let me just write it here. Hopefully that's still on the screen. Almost out of time. So that's basically like saying that the square root of x squared plus y squared plus z squared equals 5. And then the way we tend to do this is actually square both sides. And right, x squared plus y squared plus z squared equals 25. Okay, so this is the equation. And again, this is analogous to a circle. If you remember the circle of radius 5 at the origin in 2 dimensions is x squared plus y squared equals 25. So x squared plus y squared equals r squared. Okay, and if you and you can think like you can sort of check yourself that like 5, 0, 0 satisfies this 0, 5, 0. You can do Pythagorean triples 3, 0, 4. That's supposed to be a 3. You could do -4, comma 3, comma 0, 0, -5, 0. There's all these points that satisfy this. It does make a surface, and you can sort of start to convince yourself that it's really all the points map out a sphere. Okay. The last problem has some sort of harder questions, and those do come up a little bit on the homework. That's due, it's not until Friday though, but maybe I'll talk about number 10 at the beginning of class on Monday, just because it's nice to sort of start to think about some slightly harder questions. So, all right, have a good weekend. If you have questions, come talk to me. I'll stop the recording. And I will be posting more stuff, in the next 24, 40